a debate on Oriental and Old American geometry.
Welcome to the deep dive. Today we're embarking on quite a fascinating journey, really, across continents and centuries.
Yeah, we're setting aside the European Middle Ages for a bit.
Exactly. We want to explore the history of geometry in the East and the Americas. Our guide is this chapter called Oriental and Old American Geometry.
Right.
And our mission today, for you listening, is to pull out the really compelling stuff about how cultures in China, Japan, India, and pre-Columbian America tackled geometry. You know, what made them unique? What were their big achievements? Any surprising links?
That's right. And this chapter, it really does open your eyes. It shows how geometric understanding developed independently in these places.
Yeah,
it kind of challenges some assumptions, about the history of math. Shows how sophisticated thinking was, well, everywhere.
Okay, let's dig in then, starting with China.
Okay.
So the chapter highlights that early Chinese geometry, we're talking pre-15th century here, it was very, very practical.
Right. Rooted in the real world.
Totally. Solving problems like calculating areas for farming, figuring out volumes for building things, measuring distances for surveying.
Yeah, it's it.
It also points out that, okay, maybe there was some influence from neighbors, but mostly Chinese math developed on its own.
Yeah, largely independent.
And interestingly, it mentions that term Arabic mathematics. It can be a bit, well, misleading.
Yes. Because the advancements in the Islamic world weren't just from Arabs. They drew from lots of regions, lots of scholars.
That's a really crucial point. Good reminder.
In looking at early China, the written record for math, like before the pre-Qin period, it's a bit sparse.
Right, before the 3rd century BC.
But we do have evidence, early mathematical texts, astronomical texts too, going back maybe 2,000 years.
Okay.
And what's fascinating really is how important math was for officials.
Oh, right. You needed it for the job.
Exactly. It wasn't just abstract theory. Training in calculations, surveying, astronomy, it was required for government work.
That makes total sense if you're running a huge empire.
Doesn't it just...
So the chapter talks about these 10 computational canons. They became standard text later on. But it also says, the earlier stuff was really significant too.
Absolutely. Foundational.
So moving into that period, like the start of China, into the Three Kingdoms era, 221 to 280 AD roughly.
Yeah.
We start seeing more solid evidence of their geometry knowledge. Archaeology suggests they knew basic shapes pretty early.
Indeed. And you see this early interest in right-angled triangles.
Ah, Pythagoras territory, but maybe different.
Well, yeah. There's the Zhu Bi likely put together around the 4th century AD, but it definitely contains older material. It's key.
What's the cover?
It focuses a lot on the gnomon, the stick in a sundial.
Oh, right.
And the circular paths of heaven. Again, that math astronomy link.
We keep seeing that connection.
We do. And measuring heights, distances, practical stuff.
Okay, now this is where it gets really interesting for me. The Zhu Bi. It seems to have something that looks like a visual proof of Pythagoras' theorem.
That's the description, yes. Even if it wasn't a formal, step-by-step Euclidean proof.
How did it look?
The chapter describes this diagram. Squares built on the sides of a right triangle, all arranged inside a bigger square. It visually shows that A plus B SA2.
Wow, so it's like seeing the proof rather than reading it through logic steps.
Exactly. It highlights maybe a different way of understanding math, more intuitive maybe, less reliant on that formal deductive logic that, Greece became famous for later.
That is fascinating. It speaks to their observation skills, their spatial reasoning.
Definitely. And around the same time, maybe a bit earlier, you have the Juzhong Suanshu, the 9 chapters on the mathematical art.
Okay, the 9 chapters.
This was huge. A really comprehensive work covering all sorts of practical problems.
Like what?
Oh, areas, volumes, surveying, proportions, fair taxes, even solving linear equations.
This sounds like a handbook for running a society. Incredibly useful.
It really does. And the 9 chapters gives us insights into circles, too. A rule for the area based on circumference, A equals C squared over 4. And pi.
An approximation of about 3.
Okay, so practical, but maybe not super precise yet on pi.
At that stage, yeah. The chapter also mentions specific sections, like Chapter 4 on land measurement, waterworks.
Vital stuff.
And Chapter 5 on volumes of solids. There's even a problem described. Involves a town wall, a tree, the distance between them.
Let me guess, solvable with Pythagoras.
You got it. So the Zhu Bi gives us that early glimpse, right? Triangles, cosmos. Then the Juzhang Suanshu just broadens the scope massively, much wider range of applications.
The focus is really on using the math.
That's what jumps out, isn't it? These weren't just abstract theorems, they were tools for concrete problems.
And then later, in the 3rd century AD, this figure Lu Hui comes along.
Yes, Lu Hu. He wrote this really important commentary on the Juzang Suanshu.
What did he add?
Well, he refined the methods, got a much better value for pi, about 3.14159.
Wow, that's getting close.
It really is. His work also tackled volumes more precisely. Pyramids, cones, tricky shapes.
And how do you get that pi value? He used this clever method, inscribing regular polygons inside a circle, more and more sides, getting closer and closer to the circle itself.
Ah, the method of exhaustion, essentially. It's like watching the precision just ratchet up over time.
Kind of, yeah. And Louis also wrote the Haida Suanjing, the Sea Island Mathematical Manual.
Sea Island. Sounds specific.
It was, focused specifically on surveying problems. The chapter highlights his use of the principle of double measurement.
A double measurement, what's that?
It's a way to find heights and distances of things you can't reach, like a distant island, hence the name, or maybe a tall tree you can't get right next to.
How does it work, basically?
Imagine taking 2 sightings of the top of the tree or the island peak from 2 different spots on the ground. You measure the distance between your spots and the angles you're looking up. Using geometry, you can calculate the height without ever leaving the ground you're on.
That's incredibly clever.
Okay.
Especially without, modern laser surveying tools.
Ingenious methods based purely on geometry and careful observation.
Okay, so moving forward in time, between the 3 kingdoms and the start of the Song dynasty, 960 AD, what happens then?
The text suggests, well, maybe a more gradual development, still progress, but maybe not those huge leaps. Works like the Sunzi Suanjing turn up with calculations, measurement problems.
And astronomy is still important.
Oh, yeah.
Yeah.
Still a key driver for math.
Then we hit the Song, Yuan, and Ming dynasties. The 13th and 14th centuries sound like a big deal.
A real resurgence, yeah. You get figures like Qinju Shao, his Shushu Juzang, really advanced algebraic methods for solving polynomial equations.
More algebra coming in?
Definitely. And Lie's Siwan Heijing also used algebra to solve geometry problems. Yang Hui made big contributions too, including geometry.
So algebra and geometry working together.
Very much so. This period saw some really sophisticated algebraic techniques, often applied right back to geometric questions.
And then later, the Jesuits arrive, like Matteo Ricci.
Yes, in the 16th, 17th centuries, they introduced Western mathematical ideas. But the chapter emphasizes the Chinese already had this particular strength, this interest in solving equations, systems of equations. That was kind of hallmark of their tradition.
Okay, fascinating. Let's hop over the water to Japan.
All right, Japan.
The chapter says Japanese math initially, well, it followed Chinese models.
Makes sense. Close cultural ties. They adopted the abacus, this soroban, as they call it.
The Japanese counting frame
Right.
became widely used.
Very much so. But then, from the 17th century, Japan enters this period of relative isolation.
Right, the Edo period.
And they develop their own unique mathematical tradition. It's called Wasan.
Hwasan. Okay.
And Wasan is it's really fascinating. Geometry absolutely flourished, often focusing on incredibly intricate problems, circles, spheres, complex figures.
And didn't they have a unique way of sharing these problems?
They did. This practice of presenting problems on wooden tablets, sangaku,
Sangaku. Where did they put them?
they hung them in temples, like offerings almost. Mathematical puzzles for the gods and for the public.
Wow, that's amazing. It suggests math wasn't just practical or academic, but also like cultural. Public engagement.
Exactly. Almost like public art meets a math challenge. It tells you something about how they valued intellectual pursuits.
I love that image. So who are the key players in Wasan?
The chapter mentions Seki Kuhwa, Take Bakatiro, major figures, made incredible contributions. They even independently developed ideas similar to calculus, series expansions.
Seriously, independent of Leibniz and Newton.
That's what the source indicates, yeah. And they got incredibly accurate values for pi. Their geometric interests often involve things like tangent circles, figures inscribed inside other figures.
Complex arrangements.
Very. We see an early pi approximation around 3.1622, way back in the 7th or 8th century. And geometry was also used for practical things like surveying, calendar making.
Yeah.
But a really distinct area within Wasan was this idea of floating circles.
Floating circles.
Yeah, arranging multiple circles so they all touch each other in specific ways. Really intricate packing problems.
Sounds like a brain teaser.
Definitely. Textbooks like Yoshida Kushi's Jinshiki were really influential in spreading this knowledge. And those Sengaku problems, often visually stunning, mathematically challenging setups, really pushed the boundaries.
The chapter mentions Sekikufa developing something called onri.
Yes, Henri. It was basically a method related to calculus ideas for calculating the length of a circular arc or the area of a sector. He also worked on sphere packing.
Packing spheres efficiently.
Hmm?
Still a tough problem today.
It is. And Takebe Katagiro, he further developed Henri, used polygon approximations like Lu Hui in China, but took it further to calculate pi to just a huge number of decimal places for that time.
Incredible dedication. What else interested them?
They were interested in the sagitta, that's the height of a segment of a circle,
Okay.
and their solutions often involved algebra. They were tackling really tough problems like fitting circles perfectly inside ellipses.
So that Yenri principle was sort of their version of integral calculus for circles.
That's a good way to think about it, yeah. And those temple geometry problems, the Sangaku, they really became a platform for showing off mathematical skill, fostering competition. Amazing to think of math as public art, really.
It really is. Okay, let's shift focus again, westward this time, to India.
India, right.
The chapter starts way back. Indus Valley civilization. Standardized weights and measures suggesting some geometric understanding.
Yeah, and planning, construction, basic stuff, but implies organization based on measurement. Then you get the Vedic period and the Sulba Sutras.
Yes, the Sulba Sutras. These sound important.
Oh, incredibly important for early Indian geometry. They were essentially rule books.
Rule books for what?
For constructing altars for religious rituals. They needed precise shapes, precise sizes.
So religion driving math again.
Absolutely. The Sulba Sutras give geometric rules for building squares, rectangles, transforming shapes while keeping the area the same, instructions for square altars, circular altars.
And didn't they contain something like Pythagoras' theorem?
The rules resemble it, yes. Found within these practical religious instructions, long before Pythagoras himself.
Wow. And they also tried to, what, square the circle?
Yes, and circle the square, finding a square with the same area as a given circle, and vice versa. Their solutions were approximate, of course, but they were tackling these classic geometric challenges.
It really shows how practical needs, even ritual needs, could push mathematical thinking forward.
That's a key takeaway. Later on, Jain mathematics also got quite sophisticated with geometry, especially in their cosmology, thinking about the shape of the universe, like the Jambudvipa.
Okay. Then we move into the classical period, Gupta dynasty and later. Figures like Aryabhata Eifer.
Aryabhata, 5th century AD, a major figure. He gave a remarkably accurate value for pi, around 3.1416.
Very close.
And he did significant work in trigonometry, developing sine tables. His astronomical models used circles and spheres.
Then Brahmagupta later.
7th century AD. He came up with formulas for the areas of cyclic quadrilaterals, four-sided shapes inscribed in a circle. Also worked on algebra and number theory.
And Bhaskar II.
12th century. Continued building on all this work, algebra, geometry, astronomy, tackled problems with circles, triangles, various shapes.
The chapter also mentions influence from Hellenistic, Greek, astronomy, and math.
Yes, there was definitely interaction and influence there.
So going back to that Arabic mathematics point, India was clearly a huge source for the later flourishing in the Islamic world, right?
Oh, absolutely. Indian texts were translated into Arabic, Persian. They were a major contributor. But again, it wasn't just transmission. Regions like Persia, scholars across the Islamic empires made their own massive contributions too. Islamic mathematics is probably the better term to capture that diversity.
Right, got it. But back to India's own contributions.
They made really substantial, unique contributions, especially trigonometry. That was a huge development.
Applying geometry to astronomy, surveying.
Yes, calculating sine values accurately, developing area formulas. They explored spherical geometry too, and built complex instruments like armillary spheres, sundials.
Okay, a really rich tradition there. Finally, let's turn to the Americas. Pre-Columbian cultures.
Right. And here, the chapter notes, understanding their geometry is different. Challenges exist.
Because of fewer written records.
Exactly. We rely much more on archaeology, on ethnohistorical accounts, studying cultures through their own perspectives and later records. This whole field of ethnomathematics tries to get at mathematical ideas within their cultural context.
So looking beyond formal proofs again.
We have to, even in hunting and gathering societies like the Ojibwa or the Inuit mentioned in the chapter.
You see geometry there.
You do. It's embedded in their tools, their homes, their art. Ojibwa bark scrolls use geometric shapes for information, maps, Inuit kayaks, harpoons, sophisticated shapes designed for function, for hydrodynamics.
Wow, practical geometry in action.
Even basic categorization, round things versus longish things. That's geometric thinking at its root.
Then you get the big Mesoamerican civilizations. Aztecs, Maya.
And the evidence becomes monumental, literally. Their architecture, pyramids, temples shows advanced planning, real geometric knowledge.
Like the orientation.
Precisely. Structures oriented very carefully towards astronomical events. Sunrises, solstices, Venus cycles. A clear link between cosmic understanding and earthly building.
The Aztec calendar stone is mentioned too.
A hugely complex geometric and calendrical object, yes. And Maya sites like Tikal, Uxmal. Just incredible use of geometry, spatial relationships, pyramids with precise angles, observatories aligned just right.
When you mention precise angles in Maya pyramids, are there specific examples, like related to the sun?
Well, the alignments themselves often imply specific angles were intended, perhaps relating to the sun's path at equinoxes or solstices, though the exact symbolic meanings are debated. You also see repetition of geometric motifs, maybe squares, step patterns that likely held cultural significance beyond just decoration.
So it's woven into the very fabric of their building and art.
Absolutely. Geometric patterns everywhere. Art, pottery, textiles. They clearly understood symmetry, translation, other transformations in their decorative work.
Okay, and South America. Incas, Nazca.
Similar story, different context. Inca architecture, Machu Picchu, is the classic example. Masterful use of geometry to build in incredibly difficult terrain.
That's stonework.
Precisely fitted stones, often polygonal. Terracing, irrigation systems, all planned with geometric considerations.
And the Nazca lines.
Those giant geoglyphs, animals, plants, geometric shapes scraped into the desert floor. They imply really sophisticated surveying, scaling techniques. How else could they create such large, accurate figures visible only from high up?
It boggles the mind.
It really does. And again, like in Mesoamerica, geometric designs were fundamental to their pottery, their textiles too.
So looking across all these cultures, China, Japan, India, the Americas.
What's fascinating is that geometry wasn't just this abstract thing, right? It was deeply tied into practical needs. Measuring land, building stuff, watching the stars.
And even expressing religious or cultural ideas.
Exactly. And each civilization, often pretty isolated from the others, developed its own unique ways of doing things, its own significant contributions to how we understand space and shape.
Absolutely. For me, one of the biggest aha moments from this chapter is just realizing how independently these insights popped up all over the world.
Yeah.
And how much of the early stuff was driven by just tangible needs, practical problems needing solutions. Plus the sheer geometric sophistication you see in the art and architecture in the Americas.
Yeah.
It's just mind-blowing, considering the tools they had available.
And for you listening, I think understanding these different histories gives you a much broader view of mathematical thinking itself.
How so?
Well, you see both the universal aspects, certain geometric ideas seem to resonate everywhere, but also the cultural specifics, how those ideas were explored, applied, valued. It really enriches your appreciation for the foundations of geometry.
That's a great way to put it. So as we wrap up, considering these really diverse paths that different civilizations took just exploring geometry, it makes you wonder, doesn't it? What other fundamental concepts, maybe in science or philosophy or anything else, might have also branched out in these surprising, unique ways in different cultures? Ways we haven't fully appreciated yet, maybe waiting to be rediscovered or just looked at with fresh eyes?
That's a really provocative thought to end on, something definitely worth pondering.
Well, thanks for joining us on this deep dive today.
If you liked this video, please like it. Please subscribe to the channel so that we can offer similar videos.